So all participants can unmute themselves. So this will be an interactive session. Welcome everybody to our session, which is a hands-on tutorial on Ciao. And we have with us Moritz, Dave, and Melania.
Mel?
Yeah.
Mel is fine.
Hi. Yeah, sorry. So this will be an interactive session like everyone knows. So everybody has permission to unmute themselves. Only I hope that there's not too much of chaos. So please wait while people are asking their questions. And thank you so much. Thanks, Moritz, Dave, and Melania for joining us. And we can start. Yeah, over to you.
Yeah. I would first like to know who managed to install Ciao and everything successfully. So you can just unmute, or you can like open your screen and say what you want. Yeah, Dave, I'm not surprised since you work for Ciao. But it'd be really useful, or like put some button in the chat or something. Because I
think please try to use the chat window. That will be the best, less chaotic.
Yeah.
Yeah.
Because we really want to know how many people we are talking to have run it locally and how many people didn't. And since there are 3 of us, if it's only 1 or 2 that failed, maybe we can try to work that out in the chat while I start. And if it's several of us, then we'll have to work that out before we do anything else, because there's little point in an interactive session if you can't do the interactivity. Rogers, you said that you failed to install the CalDB. And so that's a good example for something that failed. I would say in general, what's probably going to be useful, since we can't all share our screen at once. If something fails for someone, you have no idea why, take a screenshot and post it in the chat. And then David, Mel, and I, if I'm not talking about something else at the time, we'll look at it and see if we can figure it out. So I see Fita managed to install, S managed to install, Prior said, Ray, you said you installed it. What about the rest? Like Bia, Sarah, Svanidu. Are you around? If so, can you type in the chat if you installed Ciao successfully or not? That's 1, 2, 3, 4. So, Rogers, you said you installed Ciao, but the CalDB failed. That's okay. We'll try to deal with that. But there'll be an extra step required. And when we get to that point, if there's any more, if it doesn't work, take a screenshot and we'll see what we can do. And also, I wouldn't be surprised if more people join us in the next few minutes or so, which is part of why I'm waiting a little bit. Because I'm kind of thinking that we want to get them in our way. Okay, but the first thing I want you to do is I'm going to post the link in the chat again. This is the notebook of examples, or an example of Chandra data, Ciao data analysis for Chandra data set that we want to go through. And so I've written all the commands essentially we're going to be using in there, such that you can copy and paste some of it and don't have to type it off and make stupid typing errors, because it'll be annoying. But each of us is going to analyze a different data set, so that you can't just copy and paste. You actually have your own data set and you're going to have your own results. So I will share my screen and starting that. So that web page is going to look a little bit like this. And so this is a Jupyter notebook. I'm sure most of you have seen Jupyter notebooks before. And as I said last time, there's different ways of using Ciao. One way is to use Ciao in the command line and do things in here. I'll bring my command line in the front and I'll do some Ciao-y things. Check Ciao version. And if I didn't mistype that, it should now, and I'm connected to the internet, which I'm obviously are because I'm talking with you on Zoom, then it should go out to the internet now and tell me this is a crucial line, my Ciao, and I installed that via Conda, and it's up to date. And so most traditionally, people use Ciao entirely from the command line. Here'll be another one. A help is a command that's terribly useful. If you type a help and then the name of something, then it's going to give you examples. DM copy is a Ciao thing that we often need. And here's the help file that you can also see on the website. But if you installed it locally, you can scroll through it here and read it without going to the internet every time. So you can work offline. Can't work right now because then you can see me on Zoom, right? But otherwise you could. So I would like everybody in some window where they have Ciao installed to type a help DM copy and see if they get anything. And if not, then we'll have to work out why. So and everybody who gets something, just say yes in the chat. And if you don't get anything or you run into any trouble, you say no in the chat. Because that doesn't require any data, it doesn't require any CalDB, it should really work for everybody. And it also tells me if I only get one yes and there really is only one person doing something, then Dave and Mel can immediately go to bed or do something else. Then we don't need three of us to watch one person doing things. But yeah, thank you. How does it look for other people?
So Moritz, for people who've installed it, you just say Ciao, right? You just say Ciao command and that's it?
Well, possibly. That depends on how exactly you installed it. That's part of why we do this exercise. If you installed it through Conda, for example, then you may want to say something like, I'm getting back to, you might want to say Conda activate, whatever the environment was that you named it, probably Ciao for 1.1, because that was my example. And then you press enter. Now I named it different. I know that was my example, but I had an environment with that name already and I made a new one just for this workshop. So for me, it would be Conda activate India workshop. And then of course I should ideally type India correctly. Otherwise it won't work.
If you type a help, then you get this whole screen, right? So how do you exit out of it?
You probably press Q. It opens the a help in whatever editor is set in your system as a default. And for most people, that's less. But it's possible to change that. It could be Emacs or VI or something else. So, but unless if you haven't done any funky stuff, then you just press Q. Okay, so we have 2 people that's successful. And I heard one person saying verbally yes, so that's 3. Who else is still trying? Yeah, Priya, I heard you. So that's 3 people who made it. And I see a few more on the Zoom though. Yeah, I know, Mel and Dave, right? I would be very, very disappointed if it didn't work for you after working for many years for Ciao. Or several years.
Afita, for all of the yeses coming through on the chat.
Yeah, we'll have 4. In fact, you can do a help, and it's going to tell you how to use the help system. So we have 4 yeses. Who else is there? Nasha, Mia. I don't know who 252. 252 Divine Yashi and Sauba and Rogers Viber. How are you guys doing? If you have a problem, do you want to share the screen or give us a screenshot? Or just unmute and tell us what's going on? Or maybe you just logged into the Zoom and got a tea and don't actually do things. That's of course is also possible. That'd be good to know for us so we know how many people we're actually talking to.
So Moritz, every time you start it, you will have to say conda activate, or should you add it to your script file?
No, you probably want to do that every time you actually want to do it.
Okay. Because I think most people have done the conda install.
Okay, there's at least one person who didn't, who's on the Windows system.
Okay.
So for the person on the Windows system, did you or can you make an account, or have you made an account at sciserver.org? Then I'll walk you through that to start that up too. Then you can do it there. So you actually don't have to watch, you can do your own data system, data thing. If you weren't able to install, that's okay. Just go to sciserver.org and you'll get a pre-install. That's going to work slightly different, but there's 2 or 3 of you, then I'll work you through that. And it's actually useful anyway, because then you can use it if your laptop doesn't have the capacity, or if you don't have the internet connection to download large data sets. So it's not a bad idea, even for other people, to see how that works. One more person joining us. Pradyasha. We are still in the process of figuring out who has it installed there. More people coming in. Okay, so I'm going to work through starting it on sciserver, and I hope that those people who said something and are just watching can follow me along and start their Ciao up there. I don't have that scripted. I don't have a video of that, so I'm only going to do that once, and after that, like, we'll have to essentially chat one by one. Okay, so if you don't have it installed, the URL, the some NASA center, so has set up a Ciao system and a bunch of other systems, but the one we are going to use today is Ciao, is the sciserver.org. And I believe that should be worldwide accessible, but of course I'm in the United States, so I can't actually test that it's actually, it's hard for me to test that it's really accessible from other places, but it should be. Okay, so that has this login button where you can either sign in or sign out or create a new account if you don't have one yet, and it's just going to ask for your email address essentially. I do have an account, so I'm going to sign in. And then you end up with this like large board where it's not quite clear of what's happening. And there's lots of different things. But the thing we want to do is we want to compute something. We want to compute a Ciao analysis. So we want to compute. That's the one we want. Compute jobs sounds very similar, but it's different. Compute jobs is for things that run a long time, that you start up and then come back the day after and check what's going on. So we're going to compute, and we first need to do a new container. They have installed everything, but we have to decide what we want. So we create a new container, we give it a name, and we select what we want. We go on this compute image, and here we pick out here SARC version 6.30.1. And if you want, you don't read that that's essentially it. You can click the CSARC data, but we won't need that today. I'm just saying it's in general, it's useful. And after you just need to change the name of the compute image, and then you can click create. It's going to take a short time, not terribly long, just a very little bit. And then you can get it on your list of containers, and with a click on it, you start it. And then it looks very similar. It's not exactly identical. It takes a moment to start up, but then it's going to look very similar to what you have on your local computer if you install Ciao locally. So for those of you who run Windows or you didn't have time, you'll get like 95% of the experience, not all of it, but you'll get 95% of the experience here. And you see that even for me, and I'm sitting in the United States, right, it takes a while, and that's because they fired up on their computer. You get this interface here. And the two things we are going to use is we're going to use a terminal and we're going to use Ciao. And so they also use Conda underneath. So I'm going to start a terminal. And in that terminal, I'll do very similar to what you just did before. Conda activate Ciao. Okay. And now I can also do check the Ciao version. And I'll hopefully find that it's roughly time. And so we are now remotely controlling this computer, but we can do almost the same things. I say almost, not exactly. And I'm going to show you one or two of those things here, but then I'll run the rest locally for me because that means it goes a little faster and I know exactly what happens and I could test it before. And you see going out to the internet takes a while.
The screen is not visible, it is white.
My screen is white.
Yeah.
Ah, okay.
No, it is visible. I can see it on Zoom over here. Are you using Zoom or YouTube? What do you?
Ma'am, I'm using Zoom.
Moritz, but can you just expand it a little bit? It's the font is very small. The font size is very small.
Yeah.
Just expand.
I'll try to make it smaller, in fact, so that there's more font to be visible. I'll make it because I think Zoom scales it, so I'll make it smaller. That should help.
Yeah, this is good. Okay.
Yep, but wrong one.
But this is your mail.
Yeah, that's not the Firefox that you were supposed to see. Try that again.
Oh, this is good.
How's this?
This is very good.
Yeah, this is fine. Yeah, thank you.
Okay, so you see that in the Ciao server, the Ciao version isn't exactly up to date, but that's okay. Okay, and so you can do now type things here like you were on your local computer. The things you want to do is you want to move to your workspace. Oops. Go into temporary and then into your account name and maybe scratch, and that's good enough, right? Oh, there's stuff already because I ran this notebook before that. Okay. So for those of you who don't have it locally, you can run things there. And since we are half an hour in and we haven't done anything, I'm going to start running the Ciao commands locally now. And if any of you hasn't been able to start it up on either side, please take a screenshot and put in the chat, and Mel and Dave will try to help you catch up. Okay, as I said, I'm going to run things locally because then I know exactly what's going to happen. Okay, the first thing I want you to do is I want you to go to, and anybody can do that wherever you are. I want you to go to this Google spreadsheet and pick, it's going to look like this. Pick one data set that you want to work on. I have picked 26133 because I like that. What we need is this ops ID here. Everybody pick one ops ID and put their name here in student name. I know some of you are professors and not students, but just put your name in, and so that everybody has their own data set to work with. And remember which one you picked. Doesn't really matter which one, just pick one. I've taken a set of data sets that are all very, very similar, but not identical. And you see, I thought 50 people would sign up, so I picked a large number of data sets, but should be enough for us, even if more people keep joining. Okay, while you do that, so for those of you working within the Jupyter Notebook, we'll now have to import the Python way to control Ciao. And I do that because then I can run everything from the notebook, and I like that. So for those of you who haven't used the notebook, you press Shift and Return to execute cells in the notebook. Shift, Return, check. Shift, Return, check. Those two are done. And then for the next, when we do things, I often have two cells on top of each other. This bottom one is how you do it in a notebook. Shift return. It's going to start download the data now. So it's going to take a little bit anyway. Depending on how fast your internet connection is and which thing you picked, it's going to take, for me, it takes about 1.5 minutes. But okay, and for those of you who run it in a terminal, yep, when it says true, we're done. True means it's successfully downloaded. For those of you who run it on SciServer, where we don't have, at least not yet, for different reasons, don't have the notebook, we can just copy this and where did my SciServer window go? Here. I can paste it into either my local terminal or into this terminal, and it's going to go and download the data. And when you run on the terminal, it says it's 33 megabytes here, and it tells you which files it downloaded. Some of them it actually found already because I downloaded them yesterday when I tried out if it worked. No module named Ciao contrib, somebody says. Did you, before you started your Jupyter Notebook, did you need to activate the Conda environment first and then start the Jupyter Notebook in there? Because when you activate the Conda environment, it sets some environment variables that that notebook needs in order to find those modules. So you probably need to close down your Jupyter, go back into a terminal, type conda activate, whatever you called it, conda activate Ciao -411, and then Jupyter Notebook start. And then you should get there. So that's to answer Afita in the chat. But while you do that, I will continue. So I said, like in my instructions, it'd be great if you can download the CalDB beforehand. And that's because the CalDB is big and takes a long time to download. It's all calibration data, as I said in my last talk, that Chandra has ever taken, that was ever needed. But of course, today, since you only picked one data set, we only need the calibration data for one day. So the easiest thing is you have the CalDB already. But if you don't, then you can run download opsid CalDB. Or if you're on a terminal, you can just take this command. Saber, you said, please post that command here. What command is that command? You mean to start up a Jupyter Notebook or?
No, so yeah. So I have actually even, the link is there to the Jupyter Notebooks. Please download the Jupyter Notebook, open it. So then you won't.
Oh, or maybe you joined later. You mean the Jupyter Notebook where you can see what I'm doing, right? Where you can, I can post that again. I posted it before, but it's.
Yeah, no, unfortunately in Zoom, if you log in later.
Yeah, I know that the things, that is again.
Yeah.
So that is the static version. I haven't done anything on that notebook, but that's where you can find the commands that we want. Okay, so while I've been talking, it's been downloading the CalDB and only the CalDB files I need for 261333 because that's the one that I picked. And in fact, I have installed the CalDB, so it found it all. If you're running in a notebook, if you're running the same thing in a terminal, it's going to say that you need to run a certain script. Now, we don't have to do that. So, for example, if I had to run the same command, and I know I was going slow.
Moritz, sorry to interrupt, but if you're running it on the terminal, then you exactly cut paste the same command, right?
Then you take the command in the cell above, I say terminal. Okay. That's, as you see, it's almost exactly, except that in Python, you need to put brackets around things and sometimes you need like You need to mark things as a string.
Okay. Yeah. So you have the terminal ones indicated. Yeah. Okay.
But if you have CalDB installed in the first place, then you don't have to do any of this. This is just for people who have not installed CalDB. And I think there was only one of them. So I hope for the person who did that, I hope that worked. If not, continue to post something in the chat and we'll try to work it out. Okay, now we want to reprocess the data. The command in the terminal would be this one, or the equivalent, this is almost exactly identical if you want to control it from Python, would be this one. I'm going to press Control Enter, and that's going to take a while. I have a laptop that's less than a year old, and it takes about 3 minutes. It might well take 5 or 8 for you. It also depends on which data set you picked, because the data sets don't have the exact same size. It's going to produce a bunch of output, and the output says which input directory you process, so you can check that you're actually looking at the right directory. And in this command, now you see here's the ops ID. Since you don't download it, hopefully downloaded another ops ID than I did, right? Mine is 26133, but I know that others, for example, Bia picked 24891. So hopefully, Bia, when you downloaded things, you changed the number that I had, the download number to whatever ops ID you wanted to download. And then you'll have to change the number here to whatever ops ID you want to reprocess. My data has been reprocessed. It also points me to this PDF file where people like Mel and Dave look at every observation that Chandra takes and checks that everything is okay. And the comments are in this PDF. So if any of you wants to open that PDF, you'll hopefully see that everything in that observation went well. Out of those 50, there's only one in there where 40 years. There's only one in there where something strange happened. I forget which one, but even that has been fixed by now. Okay. So now we've reprocessed the data and we want to look at our data. We want to see what happens. And for that, we are not going to use a Jupyter notebook. We're going to use a different program. Or let's say there's different ways of doing that. And the most convenient way is not to use a Jupyter notebook. The most convenient way is to use a program called DS9. So I'm going to start that from my Jupyter notebook by running this in a terminal, or in a Jupyter notebook, if you start with an exclamation mark, that just means you run things in a terminal. And I'm going to stop sharing once that's started up. I am going to stop sharing my Jupyter notebook because I want you to see this. Now, for those of you who are running on Sci server, you can't do this step. We'll do something else, but just hang on a minute and watch my screen. Okay, so I'll stop sharing this and instead share the other program that started up, this one. This is DS9. DS9 is a very useful program to look at FITS files. $, I saw that you just joined. We are in the middle of starting things, so it'd be great if you could open the chat where several other people are around, like Dave and Mel in particular, work for Chandra and can pick up and see where you are and try to help you out. So if you should just paste something like "I am alive" in the chat, then they're going to help you out. And if not, then we'll assume that you're not. Okay, anyway, this is DS9. So you can zoom around. This is the star we are eventually going to look at. Every single dot here is a photon, an X-ray photon. Bia, thanks for chatting. Mel or Dave will answer you in a second. Okay, so you'll also see that this is kind of cut off in the corner here. And that's because DS9 is set by default to save your memory, because not all computers have big enough memory. So it only loaded parts of that, shows part of that file. But with bin, we can choose to give it a little more. And now we can move around And you see, and you can see that we have one chip of data and there's only one source in there. Like maybe this is something, there's a couple of sources close to each other, but this is what we want. This is the bright source. And so in order to extract that bright source, we'll have to find out where it is. So I'm going to move my mouse over it. And then I can't point with the mouse to the top now, but on top left, it's going to say physical. That's the coordinates of that source that we want. And so we'll have to remember that. And of course, your source is going to be somewhere different because you picked a different observation, right? My source is at about 4,108 X and Y 4,083. And so I'm going to remember these numbers and you're going to remember some other numbers because your source is somewhere else. I'm going to spend 4 or 5 minutes on what else can be done with DS9, although we don't really need it right now. One thing we can do is we can zoom in and out. We can also filter these photons. I told you on Friday that we know for every photon, we also know the energy. And so we can decide, if we go to bin and binning parameters, we can decide to put a filter in here and say, we only want to see photons with an energy below 4,000 EV or 5,000 EV. And I will apply. And now it's going to filter it and it takes a little moment.
Download. What size level?
I know somebody said something, but I can't hear what. Couldn't hear what.
Sorry,
If that was a question, please put it in the chat so that.
By mistake. That was
Okay. It's still filtering for some reason. It shouldn't take this long. But here we go. So what it's done now, you see there's much fewer counts. It's not displaying photons that have over 5 keV. And most of those are background photons. So now our source is much better to see, but it's still the same location anyway. Okay, here's another idea how we could, or another way how we could find out where the sources that we actually want to look at. And that's something you can do without DS9. So that's something you can do on SciServer too. And I will stop sharing this and get back to my notebook. Ciao has a tool called Wave Detect that will find sources in an image. So first, we'll have to turn this event file. Remember, this event file is a list of photons into an image. And we do that with copy, DM copy, the file we come from. I'm choosing just certain energies. And then I'm going to bin that up in space in X and Y and make a new file called image.fits. And I also need to make a PSF map, a map of how big things are, how big the telescope PSF is, how big a point source would be at that point. And that command is called RTMK PSF map. And then I'm going to run wave detect, and it's going to give me a list of sources. Okay, and all these steps take a little bit. So when I started sharing, my chat was gone. I will, while I'm waiting anyway, it would be great if you could give us some indication as how it's looking and how you are, because it's supposed to be interactive, and I don't really just want to talk if nobody can follow. So if you could, give us a where did Zoom put that bar? If you could, let us know how it's going, like in the chat, or put like a symbol on your status or something.
Moritz, there's a problem over here. if you run activate Ciao from the terminal, and then from that very terminal, when you run Jupyter Notebook, then it obviously complains because it doesn't find that command in Ciao, right? So if you open that, but if you open another terminal and do it, then again, it has a problem in running the notebook.
Yeah, you have to install the notebook into Ciao.
Okay, and how do you do that?
Well, so for example,
Snapping start to pick up. So that
Okay, is it sudo snap install? Jupyter, would that work? Okay. Just share it on the Zoom chat.
there's different ways of doing it, but if you want to run, yeah, or you just run the terminal. I always have the commands how you do it in the terminal too. So you don't have to run the Jupyter. I just thought it's convenient because then we can all look at it in one document, and I don't have to share and unshare every time because a new window pops open.
This is
But you can always just run it in the terminal. And again, anybody, if you run into a problem, David Meller here to help, even if I'm talking about something else. Please post something in the chat. That's why they're staying up late at night. But my notebook is still running anyway. I still have like a dark black circle here because wave detect and PSF map takes a while.
I am running into one problem while running RT Chandra repo in the Jupyter Notebook, repro. It is giving OS error.
Can you copy and
Hello,
paste it
am
in
I-
the chat or take a screenshot so that we can see it?
Okay, let me do that.
If you install Ciao through Conda, then I highly recommend installing the notebook through Conda too. Like if you install it with, I don't know Snap, but I don't have Snap, so maybe it works for you. But if you don't have Snap installed, you certainly have Conda installed because you use Conda to install Ciao. Conda install will add a package to your existing environment. So Conda install -n will say what the name of that environment is, and then you can give it whatever you want to add to it.
Through chat, I can't copy paste the thing because that option is not available. I can just write message. So I don't know how to put that. It is showing operating system error, Chandra repro, while running Chandra repro.
Did you install the CalDB?
Yeah, it environment that shall run fine. OS environment, all the shell cells ran fine in Jupyter Notebook. But this one, Chandra RT Chandra repro, this cell is giving the error.
Can you try, instead of posting it, doing it in a notebook, do like the terminal version, go to a terminal,
Okay, okay,
open, activate Ciao in that terminal, move to the right directory and see what happens.
okay, okay, let me try.
And so I will stop sharing again. So I can share my other screen. So when you are on Zoom, in the chat, there's like, if you can see my mouse, there's this little thing where you can attach something to the thing. So I can take a screenshot however you take a screenshot, of course, depends on how your computer looks like, right? So I can take a screenshot, it goes bang, bang, and then I can attach that so you can all see my screen. Downloads it, my screenshots are set up to go on the desktop. And then it can upload them as a file. And now Mel and Dave and I could download them and you could see exactly what's on my screen, which is often more helpful. So the screenshot I took is probably not terribly useful, but because it's just of what it's just a screenshot of what I shared anyway. But you can follow the same procedure if you want to tell us exactly where you are stuck. Oh, of course, you can share your screen too, while I'm not doing that.
Yeah, so I've given participants the permission to share their screen, but obviously it has to be done one by one in case that's been done.
So if somebody is still stuck, I'm not sharing right now. If somebody is still stuck and needs help, you can also share your screen and then we can look at it directly. And if not, I can also continue. So does anybody want to share their screen to show us where you are?
I guess you can proceed. Otherwise, they can
Yep.
write on chat whenever they need.
I will continue. Okay, so I've oh, I shared too much. I wanted to share only the Firefox so you can see it better. Okay, so I've closed off DS9 again because I started DS9 with this cell and it's going to block the notebook for as long as it's open. So I closed DS9 and then these 3 cells ran through and I've run wave detect now. Okay, and now I can use either use this or this dm list command, and dm list lists what's in a fits file. It just writes what's in a fits file to the screen. And so, okay, maybe the note is not quite, make it a little wider so it fits next to each other here. It found 6 sources. This is the number of counts it has in every source. So there's a 6 count, 6.5, 6.5, 239, 7, and 10. So I clearly want to do this care for this sources is 239 counts. So as I said before, when I looked at it by hand on DS9, this is where my source is. My source is at 1408.9 and 4083.8. So I'll take those and put them in this command. So I'll do a dm extract. I'll explain it here, but again, the second cell is exactly the same. Extract will bin what I have. It's going to bin this file, and it's only going to do that for some region. It's only going to do that for a circle that is 4 pixels wide and has this center. And I'm going to bin it in time to make a light curve like I showed you on Friday. And the light curve is going to have the following name. I'm making a light curve, and clobber means I can write over an existing file. Okay, I'm going to do that. That goes fast because it's only 239 counts after all. Okay, and now I want to look at that. And that's why I really went to the notebook. I like, and just to show you that if you had installed other packages, you can use other packages in Notebook too. I like AstroPy personally to write fits files. There's many ways of doing that. I just picked this one. I'm going to import AstroPy because I installed AstroPy. If you didn't, then this cell won't work and you can either install it later or just skip those 3 cells for now. I'm going to read the light curve. It's just a fits table. And here it is. So this is a light curve now, a Chandra light curve file. It's going to have 13 bins. This is the time where it starts. This is the time where it ends. This is number of photons. Note that the first and the last bin often have zeros in them because the default time starts a little earlier than the observation and goes a little longer. That doesn't mean your star event very faint. It just means that the first and the last light bin are a little too early, and I can plot that. Okay, here's a light curve. Again, ignore the first and the last two. And then you see here light curve with error bars. And you see that within the error bars, my source is constant. Now your source, depending on which source you pick, your source may be different. There may be giant flare in there. If so, please let me know. That would be really cool. I think most of them are roughly constant, but I haven't looked at all of them by hand. Okay, next, we want to extract the spectrum. And the spectrum, we could do that again with DM extract that I used up here. But for the spectrum, we want to do several steps at once. We want to extract the spectrum, but we also want to make these ARF and ARMF files that I talked about on Friday. And so instead of doing like all this by hand, we can use a script that's called spec extract that's going to do all this stuff for us. And spec extracts needs some information. It needs like an in file, the file name. It needs to know where your source is. This is where my source is. Your sources could be somewhere else. So you're going to put different numbers in there. We're going to give the files that we have some name. We're going to pick a region where there's no source, that region. I looked at DS9, a region on my image where there's no source. It's not terribly important. We won't need that for this example, but in general, it's good practice. And here are some parameters that I'm not going to walk you through now. But if you do a help spec extract, it's going to explain you exactly what they're good for. Okay, I'm going to run that. So I'm running this version here as opposed to the unknown version. And this is from the commands after the download. This is probably the one that runs the longest because making the ARF and the ARMF is in fact hard work for the computer. And that's where it needs the CalDB files and that does some calculations. So it's going to take a moment. And so I'm just going to hang on a bit. After this, I want to fit and plot the data. And for that, we use a package called Sherpa. There's different ones. XSpec is a popular one. Sherpa is popular. There's ISIS. Sherpa has the advantage that it's installed with Ciao. So if you run on SciServer, you can switch. After you've done the spec extract, if you run on SciServer, where did my SciServer window go here? You can go on that plus and open a new notebook that says Ciao. And then from Sherpa Astro import UI, you can type that here. That's going to tell you that you don't have DS9. That's okay. We don't need DS9 any longer. And we are going to now use Python to do things with our spectrum. We can either do that here, or as I said before, I will do that locally in this window, just so I have it all together and you can see it all. Okay, we run spec extract. Spec extract tells us a bunch of stuff, mostly telling us that it didn't break and actually does things. Okay, so I'm gonna set some Matplotlib defaults the way I like them, because this is Python. We're using Python, we're using Matplotlib, we're using NumPy, and all these things we can do. I'm going to import Sherpa. I'm going to load my data. My data is called source.py. That's what we made with spec extract. So yours is probably called the same. And we're going to look at what that data looks like. My data looks like this. Yours is probably going to look very similar. And before I continue, I'm going to wait another minute or two again so that people who do that themselves can catch up. And if you have any problem, put it in the chat or speak loudly.
What are your units of temperature, Moritz, in that table you showed?
Let's just check and have it. I'll explain it in a second.
Okay.
When we actually have measured a temperature. We haven't measured a temperature yet.
Okay.
This is how a spectrum does. Who else has a spectrum that looks roughly like this somewhere? Roughly, because you're looking at other stars, so it's going to look different. I really just want to get back to the table to see what OPS-IDs we actually have. Who has a spectrum that looks roughly like this? And if you don't, I'm going to stop screen sharing so you can all share one by one and we'll see exactly what you have and can help you out. Or yeah, put your problems in the chat or anything. Yeah, still working on it. Is anybody else somewhere? Because if you don't have a spectrum, we can't do anything with it. And if you just want to listen and look at me, that's also fine. But then I don't have to stop in between, then I'll just continue. Okay, so what you see here now, this large blue box here, what you see there is plenty of bins. So I said we bin in energy. That's what I said before, right? So we have an event list. We only have 269 spectra, at least for me. You may have more, but or less, depending on which target you picked. But I only have 269 photons, and I put them in 1024 bins. So most of those bins are empty and have 0 photons in them. So this long bar that you see here is almost 1,000 bins next to each other that have 0 photons in them. So they have like a dot painted at 0, and then like then an error bar that goes from -1 to +1 or -0.1 to +0.1 or something. And so because they're so close to each other, they look like this giant bar. So that's not terribly useful because we are mostly looking at nothing here. So what we often do in X-ray astronomy is that we do a thing that we call binning data. That means we make our bins wider, so wide that there's at least 10 photons in every bin. Now that number 10 I've drawn out of a hat. Sometimes for statistical reasons, we recommend maybe going up to 15 or 20 or so. I'm just taking 10 because I don't have that many photons. There's other ways we can deal with that, but I want to do like an easy example to begin with. So I'm going to put at least 10 photons into every bin, and then I'm going to plot the data again. And this is what it looks. And you see over here, where we have a long way of nothing, we're going to get a single data point now for a long way of nothing, and the other data points are here. So really, if there's no data beyond like 2 or 3 keV, kilo electron volts, then why are we even plotting and looking at that? Doesn't make any sense, right? So I'm going to ignore that. I'm going to ignore everything below 0.5 keV because I know that Chandra is not effective in that energy range, and I'm going to ignore everything above 5 keV. And again, remember, this is the idea of your data set. That can be anything. You can call it I love donuts, or you can call it 1, but I used the number of the ops ID. So if you used a different number above, you'll have to use a different number here. Okay, now it looks like this. I ignored everything high, I ignored everything low, and now you see the individual bins here, the individual spectrum. Okay, I know this is a star because I set up the observation. I'm the PI of those observations. I know what we're looking at. We're looking at a star, and stars, the X-rays in stars are typically dominated by what is called a collisional ionization equilibrium. That means what we are seeing here is atoms or ions smashing into each other, smashing electrons, exciting the electrons in a higher level, and as they decay, they emit in certain emission lines. So now we want to compare this observed data to a model of what a certain temperature would give us, and then we try out many different temperatures and see which temperature describes this model best. And the model we want to use for that is called XSVAPAC. XS stands for XPAC. XPAC is the people who programmed this Fortran C code. So that's the one we're using. And APAC stands for Astrophysical Emission Code. Depending on what you look at, you want to use other models. Dave looks at stars too. He often uses APAC models. Mel looks at crazy stuff. She probably uses other models, like black holes or things like that don't necessarily have APAC models. Okay, I'm going to say that this is the model I want to use for my star. I'm going to, in fact, use 2 of them because I know from looking at the sun, we know that a corona, a star, doesn't just have one temperature. It has multiple components. It has a hot part and it's a cold part. In fact, it has a hot part, a cold part, and a middle part. Or really, it has a hot part, it's not as hot part, a slightly less hot part. So there's many, many different temperatures. So ideally, I would love to fit a model that has 10 different temperatures in it. But I only have 269 photons, so there's only so much I can learn from that. So for practical purposes, I'll restrict myself to 2 temperatures. If I try any more, the fit is just going to go haywire. And you can try that out. Once you have your notebook running, you can try just multiply this line many times and make it 15 different models, and you'll see that the fit won't look as well. Okay, we'll set the source. We will fit it. Here's the fit. And now we can see it prints out some information. It prints a data set. It prints some information, statistical information of how we did it. And that down here, those are the fitted numbers. KT is a temperature multiplied by the Boltzmann constant in kiloelectron volts. So the temperature of the star is 0.58 kiloelectron volts. And the second temperature for the second component I have is 2.75 kiloelectron volts. And the norm here is how bright that star is. So that's essentially the number of electrons that are emitting. I say essentially because, of course, it also depends on the distance of the star. And the X-rays don't know anything about the distance. So a star that's 4 times brighter but twice away is going to look the same brightness. So there's a normalization factor in here for the distance that we still have to deal with in a moment. Now, I want to see how well the fit worked. So I'm going to make a plot. I'm going to make another plot. I'm going to plot the data, and I'm going to plot the fit over it. And I'm going to do some extra tricky bits here. So first I do UI plot fit. That's the Shepherd command for giving me a fit. And then I want to make that look a little better, that fit. And so this plot really is a Matplotlib plot. So I'm going to use all sorts of Matplotlib commands that you can find on Stack Overflow or in the Matplotlib documentation to change things on this plot. I'm going to grab that plot, that AX, and I'm going to set the scale to log. Could do that in Shepherd, but I can also do it in Matplotlib. And then I'm going to change the and then I'm going to change the formatting of the params. I'm going to make it plot more labels at the bottom, so it's easier to see depending on the range. Matplotlib is sometimes a little careful with spelling its ink, and that could well only be the one here. So I put a couple extra labels in. I can do other things. I can do. I can set the title because that's source.py isn't a terribly useful title. So we'll call it ops ID 6133. And well, I mean, you get the idea, right? I can do all sorts of other things. I can format it, and importantly, I can also save it as a PDF file or something and use it for my publication. Now I want to calculate something that we call the confidence. There's already some like plus minus on here, but that's just a rough estimate. We want to find out now, how well do we know these numbers? How well do we know the temperatures? And so let's run that. Takes a little moment because it's trying out loads of different temperatures and loads of different normalizations, and we'll see how well they work. And there it goes. Okay, so here's the temperature in kV for the first component. Here's the norm. The temperature, see here the errors. And here's the other temperature. And you see it doesn't have an upper error. What that means is we just don't have a lot of counts. We only know things so well. And this temperature, we fit that. The best fit value is 2.7 kV, but it could also be 3, it could also be 4, it could also be 5. Because this temperature is very, very weak. You see here that the normalization is significantly smaller than the normalization of the first component. And so we just can't give an upper limit. We don't know. It could be hotter. What we can do now is for our model, we can say, what's the flux in ergs per second per square centimeter? We just integrate the entire model. We just integrate up all this curve. But you see that we don't know the models perfectly well. We only know the models up to some error. So the flux value that we have here, we also don't know perfectly well. We only know that up to some error. And the following command here is a way to calculate that error. And what it's going to do, it's going to run a lot of confidences and a lot of simulations, and gives us a simulation of what flux values we could get for different random realizations of this. So that's a statistical way, essentially a Monte Carlo way of finding out how things go. It's going to take a little bit, and it's going to spit out a distribution of fluxes. Okay, and at this point, I would like to collect all our answers so we compare our stars later. So I'm going to take this KT, this temperature, it's about 0.58. And I'm going to bow back to this table where you picked your observation in the beginning. I see Afita, Dave, Bea, a couple of people picked one. And so I'm going to put results in. This is my ops ID. I did fit it. This is the first temperature I got. This is the second temperature I got. And this is the flux I got. Okay, and the other numbers I looked up somewhere else. I go back to DS9. I looked in the RA and the DEC. And then I can go to Simbad, for example, or Gaia, or some other catalog you know about, and find out what this star is actually called. The one I picked is called HD126. And that also tells me the distance of that star. So I looked that up in Gaia and in Simbad. And so I filled in the distance here. And with the flux that I see at the Earth, I can calculate now. We can take the flux and multiply it by 4 pi and the distance squared. And so that is the flux of my star. So this is the distribution. This is the error on the flux. So that the number I picked, right, the best number, the number I put in the table, I think is 8.8. But you see, it could also be, this is a distribution. It could also well be 1 or 0.7 times 10 to the minus 12, or It could be some distribution around that. It doesn't have to be exactly that number because there's some measurement uncertainty. Okay, that's it. I fit my star. I measure 2 temperatures. I measure the flux, and now I can learn something about the corona. Yes, but yeah, I'll be delighted to have somebody else see what somebody else has been doing. Okay, it seems that you have picked a source. Either you have picked a source that doesn't have any photons. Either there isn't any photons, or when you ran spec extract, you put in the wrong coordinates.
How do
So
I fix the coordinates?
If you go up to where you ran spec extract, there you are. You run spec extract as if your source is is centered of 4108.9 and 4083.8. That's the coordinates of your source. And then you take a circle that's 4 pixels wide. But that's the coordinates of my source. So your source is probably somewhere else because you looked at a different star.
Okay, so I have to revisit it in DS9?
Yeah.
Okay.
Or if you did the wave detect above, then wave detect would also print you those coordinates. So if you ran the wave detect cells, you can just go up a little bit. Yeah, the light curve is also pointless because you didn't extract the source, right? You extracted some random region where there is 2 photons, but not the source. Okay, that's a light curve. Yeah, there's no counts in there. But if you go up to your wave detect, then you can probably see it right there, a little more up. Here we go. Okay, so you can, one down a bit. So you can either go back to DS9 or you can look at this table that's printed out in cell 15, under cell 15. I saw it when you scrolled by. You just need to look at that table there. Okay, so that's your table from your sources. And you see that source number 3 has 375 sources. So that's probably the bright star you want to look at.
Okay.
And that is located at 4106 and 4071. So those are the coordinates you want to use throughout, because that's where your star is. And if you open DS9, I mean, then you can see it. But this is a way to not have to worry about DS9 again.
Okay, got it. Okay, I'll fix it for a moment and then I'll get back. Okay.
Thanks.
Okay. Thank you.
I see Dave is also putting on his source with the original name. I'm curious now what that one is, because most of them have some HD number or some, like, not just some rosette name.
Says that was the target of the observation. I looked it up in Chaser.
Yeah, the targets of the observation, the target names are chosen in some not terribly, the target names are chosen by me in not some terribly intelligent way, because I chose 5,000 targets and I didn't want to hand check all of them. And in some cases, we didn't actually know. But I can take these coordinates for those of you who are just watching and need to be entertained in between, and I can put them in SIMBA, the astronomical catalog. I'll take Dave's Ra and deck that Dave has measured in DS9, and we will see what we find at that location. And you put a plus in here. Maybe it just has an IX number. I believe you're looking at this bright star here at 15 Tri. I don't know anything about that star, but it looks really interesting. It's probably the one we are looking at here. So let's, then we can hopefully find a distance for it. M3, maybe it's a companion for the star, maybe it's a binary or something because it's pulsating. But its parallax would be 5 milliarcseconds. So if that's the one, then it'd be 200 parsecs away, roughly. Or it could be one of those are further away. It's going to be this one. Okay, so Dave's star is about 200 parsecs away. Or in fact, 1000 over 4.8. (208 parsecs). So you picked a star that's intrinsically much brighter, Dave, but because it's further away, it doesn't look any brighter than mine. But
Oh, the one with the longest exposure time.
oh, that's what you would. Yeah. So these targets, I can tell you, for those of you who aren't doing anything, who chose just to look great, these targets are stars. And so what Chandra does these days is Chandra is getting too hot. Chandra has like a silvery space blanket around it that's falling apart because it's been in space for over 20 years. And so Chandra cools, then the sun shines from one side, Chandra gets too hot on one side. And so sometimes I just have to turn it around and look at something somewhere, move somewhere just to make like the left side cool off on the right side get hot enough again. And so 2 or 3 years ago, they asked for people to suggest targets that aren't like individually scientifically absolutely necessary, but that are randomly distributed over the sky. So if they need to look somewhere just to make Chandra cool off, at least the time isn't entirely wasted. And so what I did is I picked the brightest Rosat sources that are also in the task catalog, which is why they all have these 1RXS numbers, because I picked them from the Rosat catalog. The brightest Rosat catalogs that look like they are stars. And so we're going to study the corona of these stars. Since Dave and I, we've measured 2 so far. But we're going to look at the rest. But yeah, I can stop my screen share again so you can do it.
Yeah, because okay. I was not able to follow in the later part because I was resolving an issue
Sure.
earlier. So
That
is this
looks like a great light
okay?
curve, right?
Yeah, okay.
Maybe the star gets a little brighter at the end. Maybe there's a little flare happening. I mean, I don't know. Hard to say from those few data points, but
Okay. And what do I put here? Are
that's
these
probably going to
coordinate?
be the same.
Yes.
Either you open
Okay.
DS9 again and find out a region where there is no source, but that's probably going to work for you.
Okay. So what does this error? I think.
You put a space. Yeah, unfortunately, it can't
Here?
deal with spaces. Yeah, you just have to take that space
Okay.
out.
Okay. And then
If you do space, if it takes a space, it thinks you're giving it a second file. Whereas really you're just giving it like 2 locations, so it's a little iffy.
Okay. Okay. Got it. Okay. And then after these cells run, I'll just continue.
Yeah, then you
with
can do
this.
it again. Yeah.
Okay. Okay. Got it. Thank you.
And then you should see something.
Okay. Sure. Thank you.
Priya asked, how good is this data for mass estimates? Not at all. It's going to tell us how bright it is in X-rays. It tells us nothing about the mass of the star. It tells us about the X-ray luminosity and the coronal activity about the star. But it doesn't tell us if it's a bright or if it's a massive or less massive star by itself. So it's not a way to measure masses. It's a way to find stars that are young. If you look in a star cluster, which I know you do, because I've worked with you on a star cluster before. If you look in star clusters and you aren't quite sure if that star's a member or not, if you have a young cluster and you find X-rays, it's probably a member. If you look in the same direction, you don't find X-rays, it might well be a foreground or background star, which is what Scott does, which is what Dave does, which is what I do, and which is a project that we've worked on together. You've looked at NGC 281, I think.
Yeah.
Before.
And I think there was another one you proposed, right? Which we'll talk about later.
Sorry?
I said there's another one you were proposing. Which was it? Group which was 137?
I don't remember. Scott and I, we've proposed so many young star clusters, and other groups have too. But I've stopped proposing because Chandra is not as efficient for low energies any longer. Because there's this issue of contamination where essentially gunk and dirt collects on the CCD. That means you can't see photons below 1 or 1.5 keV any longer. And so I've stopped using that for young stars because that's where the most of the interesting emission happens for young stars. But it's still great for black holes and stuff. It's just not us stellar people. We may need the next telescope.
Yep.
Dave and Mel, feel free to say something, right? I'm done with my presentation. We're just chatting now and waiting for people to catch up. So
Yeah, the screen is free for people to share. So please share. Yeah. And Dave can talk. Yeah.
if you want to sell your science or tell us what I all do wrong in Ciao, that's your chance.
What I don't have it loaded, but why don't you show the model, the plasma model?
Yeah, I can do that. So yeah, what Dave suggested is similar to what I had in the talk, right? So this is the orange line is the best fitted model, but that's not how it actually looks. It's the best fitted model in the same bins as the data. And so in some region here, for example, between 2 and 3, we just don't have a lot of data. And so we make one giant bin. But really, the model isn't flat in there. There's things that should be happening. And so let me show you this model. Plot model. Uh, 26133. If I could type, that would help. So this is the model by itself. And in fact, what we probably want the source from this. So this is how the star looks, and probably want to zoom in a little bit. There's Shepard commands to do that, but I always forget. So I'm going to use the Matplotlib commands, because those I can use always. So this is how the model looks. It's still not the full resolution of the model, but it's a lot better than this orange line here. And so what happens is that Chandra smears that out because Chandra just can't see the details as much. And so what you see here, this is emission from neon. This one is emission from oxygen. This is emission from oxygen. And I could zoom in even more, and you'll find out that this, in fact, is not one line. These are actually 3 lines next to each other that are not resolved. And so the difference is that this is smeared out through this RMF that I tried to explain on Friday. So it looks a lot more fuzzy. And that's part of why we need to do this complicated thing, that we take this model and multiply it with the ARF and the RMF. And I can show you how that ARF looks like too. So I've shown something like that too on Friday. So you see, like below, this is 2 kV, 1 kV, below 1 kV, Chandra is today. It used to be much better, but today Chandra just isn't terribly useful any longer because there's all this gunk sitting on the detector. And then above 8 kV, it's also, you need to be really bright to see something. And then here's some statistical information about which bins and which energy range is shown in the plot. We can see the RMF2. And so I said on Friday that the RMF is how the energy gets smeared out, and that this is now for 3 representative energies in that range. So for a true energy of 1 kV, for example, the true energy of the photon is here, but we are not going to see all the photons at 1 kV. We're going to see them because there's some smearing. The detector isn't perfect. We're going to see some of them at 0.9, and we're going to see some of them at 1.1. And there's a low but finite probability that we see them even like at much lower energies. In practice, that's not terribly important because we only have 269 photons. So something that has a probability of 10 to the minus 4 is almost certainly not going to happen. Yeah, so this is how the RMFs, you see some of them even have like multiple spikes here. as escape peaks and tell us something interesting, or have something interesting to do with the detector physics. But in practice, fortunately, it's good to be aware that these things happen. If you ever see something crazy, that you know what you need to look for. But that's why we use a modeling program like XSpec or Sherpa or ISIS or Specs or something, in this case Sherpa, that already knows what to deal with and where we put models in.
Yeah, I think you mentioned something about the physics you can get from those multiple peaks, right? What could one?
It tells us something about what the detector is made of. And so that's kind of not necessarily something we need to find out. But if we looked at this very carefully, we could find out that the detector is made from silicon. That's not a terribly big surprise because we built the detector and built it out of silicon. But it tells you something. It tells you something about how the electrons escape and how the electrons get multiplied and how the electrons get detected. All that has been calibrated on the ground too. So if you build detectors looking at those things in a lot of detail is interesting in detector physics. As an X-ray astronomer, somebody has measured it, put it into the CalDB, I make an ARF, and Sherpa or XSpec or whatever program I use deals with it, and I'm going to be fine.
How does it give you a handle on the deterioration of the satellite, right? You were saying that.
Also, the way how the detector deteriorates, what we do for that, again, you don't have to do that because we already did. We get paid for doing that. And what we do is we observe an object, let's say this star, we in practice, we take something else, but we could observe this star every year. And so we don't pick a star, we take something that doesn't change much over time. And we look at it every year and say, oh, last year this was a lot brighter. That probably doesn't mean this object that we use, this neutron star, whatever we look at, this cluster of galaxies has changed, because clusters of galaxies don't change from one year to the other. That take millions and billions of years to do anything interesting. And so if they look different last year than it looked this year, that probably, or that almost certainly means that something changed on our detector. And so we compare that and say, oh, last year it was twice as bright. Well, our detector was twice as good last year, and there's more goo on top, essentially. And because we are careful people, we don't observe just one object, we observe 2 or 3, because you never know, maybe something crazy happens with one of them, and it in fact is changing. But it's very unlikely that several entirely unrelated objects change like that. And there's other ways we can check it. We can like take the same object and move it to different positions on the detector and compare those. So that's what we spend a lot of our time on. Like all 3 of us spend hours in a meeting every month where people discuss exactly that and say, oh, we've done it again and it looked slightly different. Like, that probably means the detector has gotten a little worse. Could also mean there's aliens out there who do funky stuff, but it's far more likely that our detector has gotten worse. And so all these other things are done in a similar way, right? So this RMF we get by observing something where we know the energy. Like if we can observe something with a known energy, then we can look at what shape we get, for example. Some of these things have been done on the ground before Chandra was launched, and some of them we do today by looking at stars or galaxies or neutron stars, depending on what we want to look at. And so we do that for Chandra. There's some team that does it for XMM. They're sitting in Madrid by ESA. I'm sure there's a team that does it for AstroSat, although I don't personally know those people. And maybe some of you are, or your advisors are for the students, I don't know. There's a team that does it for the Japanese satellite. There's a team that does it for NASA. That's why these instruments have instrument teams and people who worry about this calibration, because it's a lot of detail about like how thick the silicon in that detector is and how much goo we got on March and how much goo we got in June and how we estimate how much goo we had in May when we didn't make a measurement, but we do know the March and the June measurement and things like that. And so that can all be very interesting, but fortunately, most people don't have to worry about it. And in that sense, X-ray astronomy is is a little more comfortable than optical astronomy. Where if you go to an optical telescope, you are probably expected to take your own flat fields and your own sky flats or dome flats, and but at X-ray astronomy you don't have to, because we have already done that for you and put it in a CalDB. So that's and there's reasons for that, right? One is that we are a space telescope, and people can't just go up and look through and get the calibrations that they want. And time is very expensive, and it's also in space. Calibrations don't necessarily change from one day to the other. It's not like we have good weather and then bad weather. So that's why the operation is a little different from most ground-based telescopes.
Yeah, but it's a great job you guys are doing. Each time I've worked with you all, it's really, really very good. And I really love the Ciao documentation. It's really, that's what I would like to tell the participants, that we had a great session with you. That was very nice. Thanks a lot, Moritz, Mel, Dave. But on the whole, what I noticed when I used Ciao was that the online documentation and the help is really very helpful. You can, manage a lot of your stuff just using that. I think it's really very nice. So I think we are almost done, but let's ask the participants if they have any questions, so we can address the questions if they have any. Otherwise, I think it's midnight now for you guys. Right?
Almost. It's 11:30. You are on one of those time zones that are half an hour off. Oh, some and a half hour off, not like full hours, for extra confusion. But we all managed to figure it out at the right time.
That's right. Yeah. We came at 7 a.m. on a Sunday, and that was good. So it worked out. So I'll just, the last 2 minutes, if any participants have any questions, please do ask. And
Ma'am, like I'm getting some warning in between. Can I show that?
Sure.
yeah.
Should be free to share the screen.
Yeah, everyone is.
Yeah. Right now we only see your keyboard. We're also not going away. I mean, we are going away. We are not going to stay with you for the rest of the workshop. But you can always email the help desk and we'll figure it out for you.
Yeah.
Now, unfortunately, I can't read that on your screen. If you only get a warning, that doesn't necessarily mean anything. If it's an error, then we'll have to deal with it. If it's just a warning, that sometimes means that some calibration file hasn't been updated recently, or things like that.
So warnings can be ignored.
You should look at them
Even
in
you are the
general,
one-
but it's not warnings. They're just warnings. They're not errors. They could be. They're warning you of something. Those look like good spectra, though. Right? That looks like the spectrum of a star to me. And then you zoom in a little bit and you do a fit. So sometimes a warning in a fit, for example, can be if your star if you try to fit 2 temperatures, but the model only needs 1 and the second one is so faint that you can't see it, then that would give you a warning, for example.
Yeah.
So in that sense, then you can ignore it because it tells you it's just faint, right?
Sorry, Arpita seems to be sharing her camera. Arpita, can you not share your screen, desktop screen? Because the camera may be a little difficult for people to, I can pin it, so that's it, but I think this is Arpita's screen. Arpita, can you share your desktop? That would be better rather than this, because this is not legible. We can't read anything. See, on the Zoom thing itself, there's a green button which says share screen. Please use that and share your screen.
Well, that only works if you do Zoom on the same device that you also used your Ciao on, right? If you Zoom on your phone and do Ciao on your laptop, then of course that won't
Maybe
work.
she's doing that. Is that what you're doing, Arpita? You're on Zoom on the phone.
Yeah, yes, ma'am. Just a minute. I will join from the laptop.
Okay.
While Bia does that, let me say before we hang up shortly, right? Let me say that we really try to be friendly and helpful. So when it says on the Ciao documentation, if you don't know what you do, if you run into something, please send an email to the help desk. We really mean that. Right? There's people whose job it is to answer that. It's not inconvenient, and you don't have to think, oh, I'm just a student, I don't know, or anything like that. We really are, we are doing our best to help specifically if you are in a region or in an institute where there aren't loads and loads of X-ray astronomers already. Right? If somebody who works at the Harvard Smithsonian sends in a question that says, I don't know what's happening, we probably say, why don't you walk into my office and look at it? But if you have from anywhere else, essentially, we typically reply within 24 hours, unless you ask on a weekend or American holiday. Right? But during weekdays, we typically reply within a couple of hours, and most things get solved. Almost everything gets solved in some way. So please do not hesitate to send us an email, and we'll try to figure it out. Now we can read it. I think so it looks a very good spectrum down the top. The extracted source. So you clearly found the source.
But when I'm doing the plot again, it doesn't work. Oh yeah, it came.
It seems it did.
Yes.
And you see, when you look at your results there, right, you see that you have two temperature components, one at 1.3 and a cooler one at 2.88, so about 2.3. So your star is cooler than mine. And that's perfectly normal. Stars are different, right? That's the point. If they were all identical, we wouldn't have to measure them all. So feel free to put it in the table. Since there's only so few of us who worked through that notebook, we are not going to see that. But if everybody who was on the presentation on Friday had done this, we would have found out, because I admit I looked at this data before. I want to make sure that it all works. I've looked at every ops ID, but I've looked at like 30 of them or so. We would have found out that the cool and the hot temperatures have something to do with each other. So if the cooler temperature goes up, then the hotter temperature also goes up. And that has something to do with the way corona are magnetically heated. If you heat them more, both components get warmer. It's not just one. It's not one gets cooler and one gets hotter or something. Like if you compare many stars on average, you'll find that if you sort them by temperature, you'll find that as temperature 1 goes up, temperature 2 goes up too. It's not one gap, and that tells us something about the heating process. But we are not going to see that from just 3 stars, because there's a lot of scatter and a lot of statistical noise, and stars are also not exactly all identical and following that procedure. So you're not going to see it everywhere. But if enough people of us had done that, we would have seen that. I hope that gave you an idea how data analysis worked and how Ciao in particular worked, right? I picked Ciao as an example, but I said last time, like XMM, AstroSat, NewStar, that works roughly the same way.
Yeah.
If there's any more questions, if there's any more questions, email us. And if not, I wish you a good Sunday, and at least I will go to bed.
Yeah. So see you. Thanks a lot. Thanks so much, Moritz. Thank you so much. Sorry, we seem to have had a network problem, but we are all fine. So good night, and thanks so much for your help. Thanks a lot.
Thanks, Dave and Mel,
Moritz,
for joining me.
Dave, Mel. Yeah, thanks a lot, and good night. Bye-bye.
Night.
See you.
Bye.
Bye-bye. I think the life.
When I try to leave, it tells me I'm the last remaining co-host. So who wants to be a host? Just so that, or are you all hanging up because you're all in person now?
You can make me the co-host. I can stick around for a little bit. I thought I
Thanks.
was a co-host already.
Yeah, you were too, but it asked me if I want to end the meeting for all or whom I want to make co-host. I don't know. Okay, so I'll just leave the meeting, make you the co-host, and then you can figure out if everyone else is leaving.
No,
or
no,
who
you-
else.
you-
Are you all hanging out because
No,
you're
no.
all in person now?
No, you can leave. Actually, the problem is there's some network problem over here. So we can all leave. Thank you. Bye-bye.
Okay.
Bye.